Hello, this video we are going to look at the part 2 of differential amplifiers. Previously we looked at how useful differential amplifiers can be and also how op-amps have their first stage as differential amplifiers. So the input stage of an op-amp should look like this. So this gives us our first sneak peek of how differential pairs look like. But before we get into that, let's consider a simple stage common emitter, a single stage common emitter, which has an input from the mains, so either 110 60 Hertz in the United States or other parts of the world 240 50 Hertz. This has to be stepped down by a transformer and rectified and a smoothing capacitor. But as we know from our basic electronics that there will be ripples introduced into the VCC. These ripples might have high frequencies and that is undesired. Okay, so at our output we might use a capacitor to filter out the AC and get our actual output, which is the small signal amplified voltage. So we have our small signal voltage here, which is properly biased, but this voltage coming from the microphone might be plus or minus 10 millivolts. Basically a sinusoid. Where the peak amplitude is plus or minus is plus 10 millivolts. Okay, now we know from basic common emitter stage that the output looks like this: VCC minus IC, which is the bias current, but changes as a result of the microphone or the signal voltage, would also give out some small changes in current. And these small changes in current can be given as the change in voltage times the transconductance of the device. So multiply by RC, and this is going to be the output signal, which will be changing with respect to time. Placing a capacitor here will filter out this output signal or any signal changing with respect to time, and this brings out the issue of the noise. Any noise in VCC would also pass through the capacitor, as we conventionally say, because it will also be an alternating signal with time, and depending on the frequency. Usually noise have high frequencies and will easily go through the capacitor. Any noise in the cables or wires joining the microphone would also go through as high AC or high frequency noise, and also go through the outputs. So the output will look like the amplified input so this is the gain times the input plus any ripple noise. That is what we are going to see at the output after the capacitor takes out the AC part. So how are we going to mitigate this with the use of differential pairs? So this is a typical example, as we've already seen. If I place two transistors Q1 and Q2 in such a way that the output taken from Q1, I call that Vx, and the output taken from Q2, I call that Vy. Now assuming I am taking out only the small signal changes from these outputs. Then we know Vx from the previous page is going to be the amplified input. So that's the gain times the input plus any noise or ripples. Now, Q2 has no signal, but any noise from the AC or from the ripple VCC, ripples inside the VCC, would also come through if there were a capacitor placed between this and the output. So in that case, if I found the differential output, so differential, as we already know, unlike single-ended signals which we are taking with respect to ground. So if we measure the voltage here with respect to ground, then that will be a single-ended signal. And now we are taking the voltage difference between two voltages, then we call that a differential output. So the differential output Vx minus Vy is going to be all this minus that. So clearly it's going to take out the ripple voltage or any noise which is common to both outputs and give me the signal that was attached to Q1. Okay, at this point one may be wondering if we could do something to Q22 not to waste power, because as it stands Q22 is biased, and by bias means there's a constant IC going through Q2, and this constant IC is going to consume power. All that power is going to do is to help cancel out the noise. But what if we could kill two birds with one stone? What if we could add the signal also to Q2 and get somehow double amplification? So we get some amplification from Q1 and some amplification from Q2 as well, together with noise cancellation. It would certainly be better than having Q1 staying biased and just consuming power. That is only if it's going to work out well. But from the initial analysis, it might not seem so easy, because assuming I also had the amplified signal AR Vin as part of the output of Vy, then subtracting or finding the differential output Vx minus Vy is also going to cancel out the signal, and the differential output is going to be 0. Remember in the first video I said differential signals or differential pairs rejects input commons. So any signal that is common to both inputs would be rejected as the outputs, unless we can create a differential signal. At the input. So in the next video, we will look at how to create a differential signal at the input, so that we don't have our actual needed gained or amplified signal being rejected at the input. So until then, I'll see you. Bye.